Here I have a insulated sphere with non-uniform charge density. So since it's insulated, wherever we put a charge is where the charge is going to stay. It's not going to flow. So if we pack charges closer to the center and spread them out further as we move away from the center, that's what it means to have a non-uniform charge density. Our function of the density that we're going to use here is going to be that, which is as we move further away from the center, the charge density actually increases, so that I should have more charges packed out towards the edge than towards the center. Okay. Let's look at what the electric field would be at a distance r away from the center. A Gaussian surface goes around the sphere. Write out Gauss's law. And the area of our Gaussian surface is going to be 4 pi little r squared. The electric field is constant, again because the distance away from the center is the same at every single part of our Gaussian surface. The total amount of charge enclosed is the positive Q, and over epsilon naught. So if we manipulate this for electric field, we get 1 over 4 pi epsilon naught Q over r squared, which is the equation for a point particle. So even if the charges are distributed non-uniformly, it still acts like a point particle when you're outside of that sphere. Now let's look inside of the sphere. Now remember, the charges are more closely packed together on the outside, and that changes as a function of r. I'm going to call that inner radius a, so that a is less than the radius of the sphere. Okay, so we have to figure out what the charge enclosed is for this object. Now, it's not a simple ratio of the volume of the Gaussian surface to the volume of the sphere, because if we were to look at a small section within that Gaussian surface, so we take a spherical shell there that has a thickness dr, and in that spherical shell we'd have a small amount of the total charge dq. But as we move further and further out, the amount of charge is going to increase. So we have to integrate the amount of charge in each of those little shells from 0 out to our Gaussian surface at A. So this is where the challenging part of this problem comes from. All right. So rho as a function of r is going to be equal to the total charge over the total volume of the sphere, which will also be proportional to the charge enclosed over the volume of the Gaussian surface. Now, the total charge enclosed is going to be the sum of all the little dq shells. So I'm going to solve for the q enclosed. Now, we are going to replace the function of the density with what it is. So that's going to be rho naught times r. And the volume of the Gaussian surface is going to be equal to the sum of all the little spherical shells. So the spherical shells have an area, a surface area, and a thickness dr to get the volume of that shell. And the charge enclosed is going to be the sum of all the little amounts of charge that are in each of those shells. So again, that's equal to the charge enclosed. Just to get the idea, I wrote it out. I'm going to now replace the area with the 4 pi r. The rho naught stays outside because it's a constant. I'm going to have the area as 4 pi r squared, and the r right here is going to get multiplied into there, so that I'm going to get an r cubed dr. So I have an integral as a function of r. I can take out the other constants, and then I just have the integral of r to the third dr, which gives me 1/4 r to the fourth. And again, I'm summing all of those shells out to a distance a. So this is 0 to a. So that the total charge enclosed, so the 4 cancels out, is going to be equal to rho naught pi a to the fourth. Now that we have the amount of charge enclosed, apply that into Gauss's law. dA, again, is the area of the Gaussian surface, and that was drawn to a distance a. Charge enclosed. Pi cancels. These cancel 2 of those. So the electric field is equal to rho over 4 epsilon naught times a squared. If we were to graph that, up to the radius, we would get a squared function. And we know that after we exit the sphere, that it drops off as 1 over r squared, because it acts like a point particle.